So okay, so this session where we will do something a little different. We will do a new type of sessions, which would be the interdisciplinary sessions. So this type of sessions we will be linking set theory to other fields of knowledge in general, and they are not necessarily mathematics, even though this time it's mathematics probability. But like in other sessions, we will link it to other fields like biology, etc. Okay, so first before I start linking set theory and probability, we need to define what probability is, or what do I mean when I give a specific probability value to something, or what I mean when I say something is probable. So this in mathematics does not really have a clear answer. There are interpretations, but even though there are different interpretations to what probability means, the same laws apply to all three interpretations and every other interpretation up until now. So even though what probability exactly means can be a topic of debate, still all the laws of calculation of the probability itself is the same. So the most famous three interpretations are these three. First, the frequency interpretation. So what the frequency interpretation is just, or you can think of it as the intuitive interpretation. So this is just saying, like, for example, if you're tossing a coin, it has 50% chance of being heads and 50% chance of being tails. So what the frequency interpretation says that when we repeat this process a lot, we expect to get equal numbers of heads and tails. So this is the frequency interpretation of probability. When I say that the probability is half, then I expect after many iterations and after repeating this process or experiment many times, I expect the same result. Oh, to generalize the concept, if you have a certain experiment with certain probability, a probability value, then you expect that this would be its frequency or its relative frequency relative to other events that would happen, like the toss of a coin in general. Of course, this interpretation has few problems because, for example, it does not specify how many iterations exactly you need to do, or what exactly should count as a huge number of iterations. For example, if you toss a coin 1,000 times, do not really expect to get exactly 500 heads and exactly 500 tails, even if you do this 1,000 or 10,000 times. So the frequency interpretation has two major problems. First, it does not specify how many iterations exactly would count as too much iterations, and it also does not specify what variance do we allow. So, for example, if I get like one more head than tails, so does this still count as a good approximation of the probability or not? So all these are things that are not specified in the frequency interpretation. And another shortcoming of this interpretation is the actions that that cannot be represented by a frequency. So, like for example, the chance that it will rain tomorrow, there is no, or how probable it is. There's no frequency in here, so you're not really comparing it to any. You cannot really repeat it raining one day. You cannot do that. So there are things that cannot be represented by relative frequencies, and yet we can represent their probability. And so this is the first problem. These are few problems with the first interpretation, the frequency interpretation. So before I proceed, I must make clear you do not have to know all of these because this is not a probability class. This is a set theory class. But it's just, uh, I think it's better to define what probability means before linking set theory with probability. But you're not obliged to know any of the probability concepts in here totally. The second one is the classical interpretation, and this depends on the idea of equally likely things. So, for example, again, like a third eye, throwing a third eye. So, when I say that every face has equal probability, what I mean that they are all equally likely. So, I expect to see them with the same chance. A shortcoming of this classical interpretation, or this was kind of the original interpretation when the idea of probability came in the beginning. The problem is that it already uses the term equally likely, which already depends on the term probability. So it's just like using the word you're trying to define in the definition itself. So that already is the first problem. And also does not really specify how we deal with the non-equally likely things. So how can we interpret them? Even though we can calculate them, but they fall meaningless under this interpretation. The third interpretation is the subjective interpretation. So this simply said that there is no really subjective meaning to probability, and that probability can come at different values from different perspectives, and depending on what you're biased to, your beliefs, and your knowledge. So, for example, like the toss of a coin, for example. So, if I'm tossing the coin, so there are people who are really skilled who can really adjust the force they want to do to get the exact outcome. But you, as an outside observer, you do not really know that. You cannot really predict the force. So for you, because you lack the knowledge, you say the probability of heads and tails is 50-50, even though the one who's tossing the coin can say, no, it's probably heads, or it's more likely to be heads because I'm used to throwing coins or whatever. Or like if you imagine a hypothetical creature that can predict the future, for example, so for him there are no really probabilities. He knows for certain what will happen. But for you, as an observer who does not really have enough knowledge, you would work with you would start assuming a probability. So other than being certain about something, you would say that has a 50% chance of being true. So this subjective interpretation, which simply says that the probability is not a description of the thing, but it's rather a description of our knowledge of the thing. So there is no true interpretation. It all depends on what you choose, and you can choose a fourth interpretation if you'd like, but like in all cases, the same laws apply, and you can choose any of these interpretations to understand when I say this has a probability of 0.4 or whatever, then you can interpret it according to any of these three interpretations, or even a fourth interpretation if you have a fourth one. So there are certain terms when we deal with probability that we will be using. Also, again, you do not really have to know all of these, but these are just important before I start linking set theory with probability. We need to define these. So the first is experiment. So experiment is just any real or hypothetical situation that that I can describe with this probability. So experiment is whatever you perform or even imagine. So this is the first term we will be using. And then there is event and sample space. So event is what is whatever exactly I'm measuring the probability of. So for example, the coin toss, my experiment is just tossing the coin. The event is like the appearance of heads or the appearance of tails. So that would be the event, what I'm really trying to predict here, or what I'm trying to describe here, that we call an event. And then at last there is the sample space. So the sample space is just the set of all possible outcomes. So in our coin tossing case, I can say that the sample space is either heads or tails. So these are all the possible outcomes. You cannot get a third possible outcome other than heads or tails. And also in a third die, you can only get one of six faces. You cannot get a negative number, for example, or you cannot get a number greater than six. So that would be the sample space. You can already notice that in most cases, at least, or in most intuitive cases, you can have that the event is a subset of the sample space. So every event is included in the sample space. So for example, if I'm trying to calculate the probability of getting heads, then so getting heads is already included in getting heads or tails. That's already part of it. So we will not deal with all kinds of probability here. We are dealing with the simplest form where we have certain assumptions that we'll be dealing with. There are other probability cases where these laws do not really apply, but we will not be really concerned with these for now. So the assumptions are that S is an event. So S is just the sample space is an event. So you can say that this in itself has a probability. So for example, in our coin toss case, the heads or tails, the S here would have a probability of one. You would either get heads or tails. That's for certain. You know this for sure. And that would be an axiom later, but like in general, we will deal with S as an event. So we can describe S with a probability. We can give it a probability value actually. The second assumption is that if A is an event, then A dash is an event. You can already see that we're using the set language in here. So A is just the event itself. A dash is the opposite of the event not happening. Okay, so if A is an event, then we would assume that A dash is also an event. Okay, so if you have the appearance of number one on a die is an event, so we'll assume that the not appearance of number one on the die, or the appearance of would be the appearance of any other number, we'd assume that this is also an event, and we can calculate also the probability of that. And the last one is that that the union of a group of events is an event. So, for example, if I take the probability of getting 2 or 3, out of the die, that we can calculate the probability of this. We will assume that this is an event that I can describe with probability. Okay. So again, you don't really have to fully understand events and such things, so because these are probabilities. But the way we are going to link set theory to probability would just show why everything we were doing is important and why we can implement the same methods in studying something like probability theory and many other fields actually. So as probably you already know in the set theory, the axiomatic set theory, when we are constructing a mathematical system, we start with certain axioms. So axioms are just things that we assume to be true, that we do not really need proof for, or that are true by definition. Okay, so these are our basic assumptions on which we build every other thing, every other part of the whole system. So the first axiom is that the probability of any event A is greater than or equal to 0. So what is this just saying? That you cannot have a negative probability. So the probability is 0 or greater than 0. And of course it would be less than or equal 1, but like, yeah. The second axiom is that the probability of S equals 1. So S is just the sample space. And you can already see that this is in a way or another obvious. So like you have, if you are tossing a coin of heads and tails, then the probability of getting heads or tails is just certain. Yeah, certainly if you toss a coin, you'll get heads or tails. You cannot toss a coin without getting one of these, or you cannot roll a die without getting a number between 1 and or 6. So the probability that of S or of the sample space is just equivalent to 1. The last axiom is that if I take the probability of disjoint sets, so these sets A sub I, of course I is just an index, so that's just similar to the index family of classes that we spoke of. So A sub I is just a set, and then you can just keep changing the index. So assuming that all these sets are disjoint, so there are no common elements between these, the probability of the union of these sets is just the sum of the probabilities. Okay, so for example, the probability of getting 2 or 3 is how when rolling a die is the sum of probability of getting 2 plus the sum of probability of getting 3. In this case, it would be 1 over 6 plus 1 over 6, which is just 1 over 3. And of course, you can define this for any set. You can already see that we are dealing with events as sets, and we are calculating the probability of those. So you can see that we are linking all the definitions back to sets again. So this only applies when they are disjoint. We would still derive a formula when they are not disjoint for the case when you have two sets, but like if they are disjoint, then to calculate the probability of the union, you just add the probabilities. So to get the probability of an event A or B, you just add the probability of A and plus the probability of B, and like the same case with rolling a die. So there are certain theorems. We are not fully interested in their proof here, even though I can just like say it. So you have that the probability of the empty set equals 0. So how can you even prove that? So you know that the probability of the union of sets is just the sum of the probabilities. Okay, so we'll deal with the set of phi. So the probability of if so we let a1, a2, a3, all these are equal to phi. Okay, so if I take the probability of their union, that's just the sum of their probability. So first you notice a few things. First, that the union of phi is just phi, or the union of empty set is empty set. So if you take empty set, union empty set, that's just the empty set already. So if you proceed through this further, you'll find that the probability of the empty set plus the probability of empty set plus the probability of empty set any number of times equals the probability of empty set, or that n times x equals x. And this only happens when x is equal to 0, right? So what's happening here is that I'm adding the probability of phi plus the probability of phi plus the probability of phi any number of times, like n is just any number of times, and all of that would equal the probability of phi also. And this only happens when the probability of phi equals 0, actually. The second case is that the probability of A dash equals 1 minus the probability of A. And this already can be seen because like you have that A and A dash are first disjoint, and adding these two gives you the S actually. So the A union A dash gives you the whole sample space. So for example, if you're rolling a die, the probability getting one and not getting one gives you all the possible outcomes. You cannot have a case where you neither get one nor not get a one. You'll have to be in one of these two cases, right? So you can already see that A union A dash is S, and you know that the probability of S is 1. So the probability of A plus probability of A dash is 1. So, and just moving things from the left hand side to the right hand side, you can easily see why this is like obvious. So, and the last theorem, and this one we would actually prove here. So we'd use this set we would prove this theorem is that if you have A is a subclass of B or A is a subset of B, then the probability of A is less than or equal to the probability of B. So this theorem we will prove because it shows like that even while dealing with probability theory, you would implement the same method of proofs that we were using in set theory. And the same thing applies to almost any field of mathematics or almost every non-arithmetic field of mathematics in general. So here I proceed by trying to show that B is the same as A union B intersection A dash. So, or simply that if X belongs to B, then it belongs to A or it belongs to B and not does not belong to A. So, how do I know this? So first, here of course we have the case that A is a subclass of B. Okay. So the easiest way to visualize it is like now we can imagine a circle and inside is another circle using the Venn diagram. So that would be then the inner circle is just A and the outer circle is B. So that's just A is a subset of B. So for something to belong to B, it has to belong to one of two things, either inside A or it's in B but not in A. And that's just what this is saying, right? So I can say that B is the A and everything that's in B and not in A, right? So so this is just what this is saying. And so I can say that B equals A union B intersection A dash. So this is the part that I'm trying to prove. Okay, so this is simply because A is a subset of B. So I have that if something is in A or if something is in B but not in A, then that gives you the whole of B. That's every possible case in B, right? So so you can already see that. So you can already see the use of the same methods we used in set theoretic proofs again implemented here in probability theory. So now we have that, and then you would proceed further to find the probability of B equals the probability of A plus the probability of B intersection A dash. So this is just applying the our axiom, right? So this is just applying this axiom that the union of sets, if to get the probability of a union of disjoint sets, we just add their probabilities. So first, of course, this is disjoint because you cannot have something both belong to A and not belong to A at the same time, or something that belongs to A and not and belongs to A dash at the same time, right? So you can see that A and B intersection A dash is these two sets are disjoint. There are no common elements. You cannot have something built in A and not in A at the same time. So since these two are disjoint, I can simply add their probabilities. So the probability of B is just equivalent to the probability of A plus the probability of B intersection A dash, right? I also know from my axioms that the probability of any set is greater than or equal to 0, right? So I have that the probability of B intersection A dash is greater than or equal to 0. So you can notice here that the probability of A plus something, this something is 0 or bigger, is already greater than or equal to A, the probability of A. So for example, if you have x plus y, where y is 0 or bigger, then certainly x plus y is greater than or equal to x, right? Because at the worst case, or at the smallest value for x plus y would be 0, and you will have x equals x. At any other case, if y is greater than 0 by any value, then x plus y is greater than x, right? So you can see that in any case when y is greater than or equal to 0, that x plus y is greater than or equal to x, right? And so this is just the case here. We have that the probability of A plus the probability of B intersection A dash is greater than or equal to the probability of A, right? And this part, the probability of A plus the probability of B intersection A dash is B in itself. So this is equivalent to B. So overall, you would have that the probability of B is greater than or equal to the probability of A. So if this does not make any sense, please leave in the chat. So, so this is just the same methods we used before. We are proving the equality of two sets, and then based on that, we are applying our axioms in the probability theory, and we reach our new conclusion already, right? Okay. S- So the second theorem that we will be proving is that the probability of A union B equals in this case A and B are not disjoint or are not necessarily disjoint. Okay, so in the first case that that applies only when the sets that we're dealing with are disjoint. So I cannot apply this rule unless the sets are disjoint. Okay, so if A and B have any intersection, this rule would not apply, right? And that's why when adding these two probabilities, I had to prove that A union B intersection A dash are these two sets are disjoint. And that's just because X cannot both belong to A and A dash at the same time. So the idea of just summing the probabilities only applies in disjoint sets. But when we do not have a disjoint set, when we have these two sets and they are not necessarily disjoint, then this is how we calculate the probability. The probability of A union B equals the probability of A plus probability of B minus probability of A intersection B. And actually, also this theorem we are going to prove because it again, I would say its proof is really elegant and it really depends on set theory. Like in a little of depth, even though it's not really hard, like we took the concept that we will be using in this proof. However, I find that it's a good illustration of why the proofs in set theory are really important, or why set theory in general is important. So first I have A union B equals B union A intersection B dash. So this is the first thing that I have with me. And why this is this true? So first I can notice that B is just B intersection A dash plus A intersection B, right? Union A intersection B. So if something belongs to B, then it either belongs to B and not to A, or belongs to both A and B, right? So these are the only cases that something can belong to B. So if it either belongs to B and A at the same time, or belongs to B but not to A. So I can already find that this translates to, so I can translate this B into X belongs to B and not to A, X belongs to A and B, and the third case here, which is the union, X belongs to A and not to B, which is just all the possible cases for X to belong to A union B. So if you take a look at every case here, so you have that case of A intersection B dash, so that is A, X belongs to A but not to B, right? This case, X belongs to B. So X belongs to B either when X belongs to A and B, or when X belongs to B and not in A. So you can find that this is already all the possible cases where X can belong to A union B, right? Also, in order to visualize it, you can just draw its Venn diagram. But like, yeah, so, and then the next thing that we notice that A equals A intersection B dash union A intersection B. So now I think this is already obvious because here you have everything in A that's not in B and everything that's in A and B, which just gives you A. Well, which actually the same idea in the first part, but this is just this simpler version where you have only one set. So you can already see that if something is in A, and if you take everything in A and not in B, and everything that's both in A and B, that gives you just A. So that's every possible case for A, right? Further, you can notice that these two sets are disjoint because if you take X belong to A intersection B dash, then you have X does not belong to B. But then it cannot belong to both A and B at the same time because it does not belong to B. And if X belongs to both A and B at the same time, it cannot not belong to B. So these two sets are disjoint. There is no way that X can belong to A and not B, and at the same time belong to A and B, because it cannot both be in and not in B, right? So you can see that these two sets are disjoint, and since they are disjoint, I can deal with them with my older way, right? With the idea of summing probabilities. So the probability of A equals the probability of A intersection B dash, which is just the first set here, plus the probability of A intersection B, just the second set here. And that's because these two are disjoint. Now I can subtract the probability of A intersection B from both sides, right? Or I can just like transfer this to the left hand side and change the sign. So this would just give me the probability of A intersection B dash equals the probability of A minus the probability of A intersection B. So I just here played with just algebra like any ordinary equation that we have. So in order to reach the second part. So now what we have is that A union B is just that the probability of A union B is the probability of B plus the probability of this part, right? Because again, B and A intersection B dash are disjoint. So now if I have the probability of B, then what's left to me is to find the probability of A intersection B dash, right? And that's already what we found here. So the probability of A intersection B dash is the probability of A minus the probability of A intersection B. So now I can add the terms in the first equation, like the probability of B. So I can add the probability of B to the second equation, right? And this will give me just the probability of A union B. And so using what we have in 1 and 2, I can say that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Again, this is just the probability of B and the probability of A intersection B dash. But I have that the probability of A intersection B dash is the probability of A minus the probability of A intersection B. So I'm just substituting what I found into the first equation. And this just gives me the conclusion that I need. So you can already see that we are depending on the idea of the equality of sets and when are two sets equal. And we are using the same methods of proof that we had before in order to reach conclusions about how we can calculate probabilities of different events at the same time. So that's actually the last proof. And now there are two exercises. The first is supposed to be very easy. So like type in the chat the answer. Okay, good. So the solution is obviously just 1. Now the second one, assuming that the probability of A is 0.25, probability of B is 0.35, and the probability of intersection B is 0.15. What's the probability of B union A dash? So this is not just B union A, that's union A dash. So again, should have some time to think about it. Okay, so so the answer would be 0.9. So first, we would put the general formula. So we have that the probability of B union A dash is just the probability of B, but the probability of A dash minus the probability of the intersection. So that's just the law of B of A union B is just B of A plus B of B minus the probability of the intersection. Then I can say that B equals B intersection A union B intersection A dash. And this is just because if B, everything in B and both B and A, and everything that's B but not an A, that just gives you B in general. And also these two are disjoint because you cannot have something belong to both A and A dash at the same time. So these two sets are disjoint. So I can say that the probability of B equals the sum of these two probabilities because they are disjoint. And then again, moving from the right-hand side to the left-hand side, I can say that the probability of B intersection A dash equals the probability of B minus the probability of B intersection A. And then I just can substitute into the equation. So I would have the probability of B union A dash equals the probability of B, which is just 0.35, plus the probability of A dash. And I have from the axioms the probability of A dash equals 1 minus the probability of A, right? So that would be plus 0.75 minus, I have the probability, these two probabilities, right? So that's just 0.35 plus 0.15, which would then give me 0.75 plus 0.15, which is just 0.9. So does this make sense? Also, sorry, this spot should have been minus, okay? So this sign is minus, and that's why it became plus after the subtraction, right? So this spot, this sign should have been minus sign, this sign right here, okay? So this is just the solution to this problem. So yeah, again, using the same methods we used in the previous theorems. So I think that's it. And if you have any questions, feel free to ask them.
Okay, so that's the wrap for this lecture, but we do have a bit more time today. So we thought we'd do a little bit of review for previous lectures in that extra time.